sp hybridization of carbon. Now, just to explain how these orbitals are mixing again, carbon has 6 protons. You expect it to have 6 electrons when neutral. Electronic configuration is 1s2, 2s2, 2p2 with 4 valence electrons in the unfilled second shell, n equals to 2. So you have 4 valence electrons. Those are the ones used in bonding. So again, we'll just show the valence electrons here, ignoring the 1s2 electrons somewhere here. So let's focus on the 2s and the 2p. You have 4 valence electrons, 1, 2, 3, 4, shown, maximizing the spin. Now you're going to promote an electron from here to where the space in the 2pz, probably. Call this 2px, call this 2py. So 2pz now has an electron before he was empty. Okay, 2px, 2py. All right. So now momentarily here, this is very, very temporary state. Momentarily, this is what you're going to get, but because you moved an electron that had s characteristic to an orbital that has p characteristics, you're going to hybridize them or mix the s and the p. Since your goal is just to have 2 atomic orbitals mixed, you will probably just take the 2s, assume this was the 2s, and maybe the 2px, and then keep 2py and 2pz at the same energy. When 2s mixes with 2px, their energies will be average. See how 2px is high there and 2s is down here. They'll meet somewhere in the middle, and those two become same energy. We call that degenerate. So focus on the orbital types that were mixed. It's an s and a p. Now, since we mixed 2 atomic orbitals, we're going to expect to have 2 hybrid orbitals. That is the rule all over the place in this chapter. So 2 hybrid orbitals result per carbon atom. So if you're looking at a carbon, it's going to have an sp on one side and an sp orbital on the other side, and is going to use that to bond with something else like hydrogen or even another carbon. We'll see that shortly. Now these blue orbitals right here, they were not used to make the hybrid orbitals. They are called unhybridized p orbitals. So each single carbon should have unhybridized p orbitals, and probably they're going to be 180 degrees up and down like that, but 90 degrees to the sp. So these are 2 p orbitals that were unhybridized, the ones you see here. Probably the first one is the 2pz, and the second one is the 2py, based on the orientation on the Cartesian plane. Now this is just one carbon. So suppose we put 2 carbons together, what will we see? Let's illustrate that. So suppose we have 2 carbons. Each of these carbon has the sp orbitals. So I'm going to exaggerate the overlap, but this is sp for this first carbon 1. This sp, you know, there are 2 hybrid orbitals per carbon, so sp and sp. Right here you have what we call the covalent sp-sp sigma bond. All right, and then each of these has the 2 unhybridized p orbitals, 90 degrees to the carbon, which of course I call this 2pz, and then this 2py. So this is the other side of 2pz, this is the other side of the py. So similarly, this one will have a 2pz unhybridized orbital, that's your 2pz, and then 2py on the other end of 2py. So remember here where the orbital is overlapping, the orbitals are overlapping, head-head overlap. That's where we are getting our sigma bond, covalent bond. So now in space, those orbitals, p orbitals that were not hybridized, talking about these two, 2py, 2pz, these ones, they will overlap, but side-side overlap. So you're going to have a side-side overlap of the p orbital. So you can have a pz overlapping with pz. That gives you a pi bond. And then you will have the py overlapping with py, giving you a second pi bond. Okay? So you have two pi bonds in addition to the sigma caused by the sp-sp. So when these come real close, you get a pi bond. There you go. Let me change the color here, maybe to green. When py overlap, maybe they come real close, you're going to get another pi bond. Okay? So the resulting is you have two pi bonds from the pz overlap and the py overlap, and you have the sigma. So the resultant structure is going to have the two carbons. They're going to have a pi bond here. There's a sigma bond in between. And then the blue here will represent the second pi bond. So this is the second pi bond where you had your pz overlap, side overlap. And then this one right here is the first pi bond where you have your py side overlap. And then the sigma bond in between, we know that these two carbons are sp hybridized. That would be the sp but sigma bond. Okay, so that tells you that you made a triple bond. For every triple bond has one sigma bond plus two pi bonds. The pi bonds are always made when two p orbitals come real close, side-side overlap. The sigma bond is made when orbitals are overlapping head-on, like what you see here. That's the sp sigma bond, the red one. So that is what's happening with the triple bond, but we can go online and I will show you more details. But before I go there, you can also have a hydrogen. Okay, you can also have a hydrogen. The hydrogen will bond on the other side. Here, if this is a hydrogen, he brings the s orbital. So the bond here will be the sp sigma bond because it's headed overlap. Same thing, I can have a hydrogen here. This bond right here is between the s orbital because hydrogen has one electron, one electronic configuration. So you get a sigma bond here, head-head overlap of the sp and s orbital. Okay, so you get a covalent bond. See, now chemistry can explain everything. This chapter is on structure and bonding, and you can see how we made a triple bond so fast using orbital overlaps. Bottom line, the pi bonds, the green and the blue, are always made by pp orbitals doing side-side overlap. Sigma bond, the red one, is head-on overlap. So I can have the hydrogen here now to show you. Okay, so this is a sigma bond, that is an sps sigma bond, which is similar as this sps sigma bond, s coming from the hydrogen. And then this red one is sp sigma bond. The pi's are always pp side overlap. And that explains to you how the structure of acetylene is drawn and why it's drawn with a triple bond in between. This molecule is used in welding. The carbons here are sp hybridized, because you can see if I focus on this, it's bonded on 2 atoms. So 2 atomic orbitals involved, so we just say sp, and it's going to be linear. The bond angle is going to be 180 degrees, and so on and so on. We can explain so many things. Now let's go online and visualize the bond formation of the 2 pi bonds and the sp-sp. So we come here. I want to form that molecule. So I'm going to assume these black balls are my carbons. And because we say they are sp hybridized, I'm going to put SS on each. And then I'm going to put P to that. Now on the left, we have sp hybridization. Here, okay, the thing is I can click hybridization to see how this is going to hybridize. See, it gives me 2 hybrid orbitals. We do the same thing on this side. I combine my S and my blue P. I hybridize. It's going to give me 2 hybrid orbitals. But now in the middle, you get what we call the sp-sp sigma bond. What you're looking at here in red, sp-sp overlap, it gives you a combination of molecular orbital combination that gives you now one big balloon that you can see in there, this one, sp-sp sigma, because it's head-head overlap. However, you have 2 unhybridized p orbitals per carbon. You see these 2 guys, every carbon has these 2 that are unhybridized. So let's put the 2 blues. So I'll put one unhybridized there, and I put another unhybridized there. You see, immediately they make the pi bond. That's 1 pi bond. Then I put the second unhybridized. See how it's staying 90 degrees to the green. And the second unhybridized, immediately, again, they make the next pi bond. And you can see. So this is a pair of pi bonds. So the top blue and the bottom blue, that's 1 pi bond. The left blue and the right blue, that's another pi bond. So the center of it, that is the sp-sp sigma, and then you have 1 pi bond and 2 pi bonds. Don't count the blues by themselves, they are paired. So you have a triple bond. The green, this pair horizontal, and this pair on the vertical gives you 3 bonds, triple bond. Okay. Now the moment I rotate 1 carbon, definitely the pi bond breaks because it has to be side-side. See, it disappears. Why? If I rotate this, it's out of phase. The p orbitals don't see each other in space. See? So I have to make sure that they are not at an angle. The moment I put it aligned, then I get the p orbitals, which is why the pi bond is made by side-side overlap. Those p orbitals must be parallel for them to overlap. Now my hydrogens would come at the end here with an S and another one here with an S. It will not allow me because I don't have a dot here. But imagine a hydrogen coming here with the S, a hydrogen coming here with an S, so you'll get SSP, SSP. That's the idea. So that is the acetylene, and he ends up having that structure with the hydrogens in the end, and you have 3 sigma bonds. So this is the structure we ended up with. Let me do it this way. So you have 3 sigma bonds and you have 2 pi bonds. That's a pi, that's a pi, and then this is sigma, sigma, sigma. I think I've explained how all those sigmas and pi's are found. And this is another view showing you that much of the electrons in acetylene are going to be somewhere in between the molecule because that's where you have more electrons. These are 3 bonds. Each bond has 2 electrons. So you expect 6 electrons around that area, which is why this area is more orange. For the color code of this cartoon representation diagram, whichever way you want to call it, global representation of charges, where you have orange color, it means there's a lot of electron density here. And it's true because of the triple bond, which carries 6 electrons. And the blue is going to be the side where you have partial positive charges. And in fact, that hydrogen at the end is acidic. Usually acidic species have partial positive charges or full positive charges. The terminal hydrogens are acidic, which is why it's blue. Okay, example 10.5 is asking us to describe the bonding in formaldehyde molecule whose Lewis structure is shown. We did this before. I know that this carbon right here is surrounded by 3 electron groups or 3 atoms. So if it's 3 atoms surrounding the central atom, which dictates the shape of the molecule, I expect, so right here, expect 3 atomic orbitals. If I expect 3 atomic orbitals, then I would expect combination or hybridization of spp, 1, 2, 3 atomic orbitals, and that tells me that the carbon is sp2 hybridized, which means the valence electrons coming from the carbon, remember carbon has a valency of 4, so I'm showing the 4 dots. Those 4 dots are residing in sp2 hybrid orbitals. You know that hydrogen has 1 proton, 1 electron, so it's going to have just 1 s1. So the s orbital comes from the hydrogen. But before that, let me make sure that you're seeing my 4 dots clearly here. So 1, 2, 3, 4. All right, so each hydrogen is going to bring its s orbital to overlap because sigma bond, covalent bond is made by orbital overlap. So I expect here the hydrogen is bringing the s. So the sigma bond here is sp2, s from the hydrogen, sp2 from the carbon, similar to this sigma bond right there. Now, where you have the double bond CO, one of them is a sigma, one is pi. Let's presume that this is pi. This pi is formed by side-side overlap of an hybridized p orbital from oxygen and carbon. They give you a pi bond. So pi bond is always made by pp overlap. Remember, we are describing the bonding in this molecule. The other one is a sigma bond. I'll ask you, what is the hybridization on oxygen? You have 2 lone pairs in oxygen and you have a carbon. So you have oxygen bonded to 1 atom, which is the carbon, and then you have 2 lone pairs. So that gives you 3 electron groups. Again, that oxygen has to involve 3 atomic orbitals, so the oxygen is sp2 hybridized. So the sigma bond is made by an overlap of an sp2 from the oxygen and an sp2 from the carbon. So that sigma bond is sp2 sigma bond, covalent bond. Okay. So I've described everything. This is a pi, that's a sigma, this is a sigma, and this is a sigma. Carbon is sp2. If I draw formaldehyde, the bond angle is going to be roughly 120 degrees because that relates to the sp2 hybridization in carbon. Okay, so which is why they are telling you to assume oxygen is sp2 hybridized. But I've shown you why it's sp2 hybridized. Okay. So in details in terms of atomic orbitals, to confirm the hybridization of carbon, carbon needs to bond to 3 things and then have one unhybridized p orbital to use to make a pi bond. So promote this here. Okay. Once you promote that there, what you're going to get is this. The 2s will be left with 1, and then those p's each will have 1 electron, but only let me use green. Only 1 s and 2 p's are going to do the hybridization. Okay, so assume this is pp, which gives you this 1s and 2p's, maybe px and py are participating, while pz is not participating in hybridization. So this makes the carbon sp2. For oxygen, similar thing. Oxygen needs to have 2 lone pairs, and it bonds to one atom, so he just needs one orbital free. So this electron is going to be promoted there. When that happens, you'll temporarily get the S with 1 electron, and then the P with the 3 boxes will have 2 boxes paired up. One is not paired up. And since we need to make a pi orbital, a pi bond, only these are going to take part in hybridization. This one will be unhybridized. Just like we did with the carbon, the PZ was unhybridized. So when these two combine, they make a pi bond, the pi bond that you saw here. That's the pi bond that you saw. And then the other one is just going to be a sigma bond. And since this is sp2 and this is sp2, you can see that right here, you are left with an S. Maybe these are px and this is a py. Pz not hybridized. So oxygen is sp2. So oxygen is sp2. So the sigma bond is sp2, sp2 sigma bond. It's written as sp2 dash sp2 sigma bond. Okay. Here they are showing you the pi bond. They are showing you the 2 lone pairs on oxygen. Okay. And in between right there, that's our sigma bond. The same pi bond you see up there, it's usually a pair, is the same one down here. So you have 1 pi and 1 sigma to the oxygen and the carbon. And then the carbon stretches out with its sp2 to combine with the S from the hydrogen to give you ssp2 sigma bond right there. That's a sigma. Same thing here, you have sp2. The hydrogen brings the S. You have ssp2 sigma bond right there. Okay. In conclusion, the lone pairs are going to be in the sp2 orbitals of the oxygen. The pi bond is from pp, overlap, the P from the carbon, P from the oxygen. The sigma bond here is sp2, sp2, sigma bond. Here, this sigma bond is formed by overlap of the s orbital from the hydrogen and sp2 of the carbon. So that sigma bond is ssp2. Same with this will be ssp2, the S from the hydrogen, sp2 from the carbon.